Hello, my friends. We are going to be looking at the one-dimensional wave equation, and we are still looking at a series of partial differential equations, applications to engineering, and that is engineering mathematics. So now what we are going to do is an analytical solution. We are going to go step by step and until we come up with a general solution for the one-dimension wave equation. So if we consider, for example, an elastic string which has got elastic properties in a way that it obeys Hooke's law, we'll find that if we tie that string, we fix both ends, let us say here and there. So this is at x is equal to 0, this is at x is equal to L. Now this is in any undisturbed position. Now what if we hold in the middle, we displace it by stretching and then we release it. So when we release it, it is going to vibrate, and then the equation that describes the motion of waves within this string is actually what we call the one-dimension wave equation. That is if we consider just one dimension. So that is along the x direction. So this is going to look like this. If you have it in this way, and then once you stretch it, okay, once you stretch it, then here, this is at x is equal to 0, this is at x is equal to L, you'll have it describe such kind of a motion. So this is u x of t. So what is the one-dimensional wave equation? So the wave equation, which describes the motion of waves within this string as it vibrates, is given by, going to be given by del, the partial derivative, the second partial derivative of x will equal to 1 out of c squared, then times the second partial derivative of u with respect to t. So this is what it looks like. Another one can also say this is u xx equal to 1c squared, then times utt. Yes, so using this notation, that's how we can also write the 1D wave equation. So now let's look at the solution. The solution, we are going to use a method of separation of variables. Method of separation of variables. So what does this mean? We are going to, first of all, look at a number of conditions. And we are saying the position of any point P on the string. This is what we are meaning. Any point P on the string, okay, depends on its distance from one end and on the instant time. So its displacement u at any time t can be expressed as the equation of motion, which we have already stated here. Del 2u del x squared is equal to 1 out of c squared del 2u del t squared. And that is the wave equation, or the equation of motion of the waves within, or of the wave within the string. Now the boundary conditions that we are going to consider, obviously we are going to say that when we have x is equal to 0 and x is equal to L, the displacement is going to be 0, because you can see here the string ends are fixed. They are fixed. So there is no motion here, there is no motion here. So that is very important. And of course, let me say the boundary conditions. We are saying u0 t is going to equal to u u of L t, and this is equal to 0. Then we shall also have initial conditions. So initial condition that we are going to consider is going to be the fact that when you have ux of 0 at t is equal to 0 seconds, this is going to be a function of x. And that function of x, usually, it can be given, and you use it later on to, during the process of analytical solution, you'll find the application where this fx is going to be helpful. So let's move with our separation of variables, and maybe the other initial conditions, actually, then another second initial condition that we always need to take care of is del u del t at t is equal to 0 is also going to always be given, and this is equal to g of x. This is another function of x that is going to always be told about. So you need these two initial conditions and these two boundary conditions for this one dimension wave equation. So let's go. Let the trial solution be u x of t is equal to x of x, then t of t. So for simplicity, we are going to say u is equal to x t. Yes. So when we do partial differentiation of this u with respect to x and with respect to t, this is what we are going to have. So we are going to have del u2, then del x squared is actually going to equal to x double prime t, and then if we are talking about del 2u del t squared, this is going to be x t double prime. So when we substitute this in this equation, if I call this equation I, okay, then I call these ones 2. So I'm going to put 2 in I. So when I put 2 in I will have x double prime t, which is equal to 1 out of c squared, then x t double prime. So what does that mean? I am going to use separation of variables here, and I will have x double prime divided by x is equal to 1 out of c squared, then t double prime divided by t. Now, what if I say let x double prime out of x equal to 1 out of c squared, t double prime divided by t equal to a constant, okay? Let this be a constant, say nu. If it is nu, then we are going to see how we can modify it for us to have solutions that we are interested in. Now, if that is the case, I will have x double prime is equal to x nu. Okay, that is one side. So I will have x double prime minus nu, then x is equal to 0. That's one. Then I will have also t double prime is equal to nu t, so that I have this is also having c squared. So t double prime minus nu c squared dt is equal to 0. So I consider this to be equation 3. So what I'm going to do is to apply cases. So case 1, when nu is greater than 0. So when nu is greater than 0, this is what I'm going to have. my x is going to be, first of all, I will talk about the auxiliary equation, whereby m squared is going to be, m squared is going to, I will have m squared minus what? Minus mu. Okay? So, and let us assume, for simplicity, let nu equal to p squared, so that I have m squared minus nu is equal to 0, so m squared minus p squared is equal to 0. So which would give me m equivalent to what? Equivalent to, I will have plus o minus p. So x is going to be a exponential of px plus b exponential of minus px. Then t will have the same, except that we shall just change the constants so that we have c. Let us call it, maybe we call it c1. Okay, exponential of t of p. Actually, this is going to be pct. Okay, plus d exponential of negative pct. What would be the solution? The solution would be u is equal to xt. This would be a exponential px plus b exponential negative px. Okay, then times c1 exponential pct, then plus d exponential negative pct. Now let's apply boundary conditions. So apply boundary conditions. When you apply boundary conditions, we find that when x is equal to 0, u is equal to 0. So when we put in 0 here, this is what we are going to have. This implies that I'm going to have a 0 here, a 0 here, so I'll have a plus b, okay, into c1 exponential of pct, this is small p, and plus d exponential of negative pct, everything equivalent to 0. So what does that mean? For this to hold for all values of t, then this component does not equal to 0, but a plus b can equal to 0. A plus b can equal to 0, meaning that a is equal to negative b. So we apply another boundary condition. Another boundary condition is when you have x is equal to L, so UL t is also equal to 0. So we substitute in here. When we substitute in those values, what is it that is going to happen? I'll have you will have a exponential of p L. Then remember I said a is equal to negative b and b can be negative a. So I'll have negative a exponential of negative p L. Okay, and this is multiplied by c1 exponential of pct plus d exponential of negative pct. And if this is equal to 0, remember we have a into exponential of pl minus exponential of negative pl. Then times c1 exponential of pct plus d negative pct. So is this going to be 0? Okay, so now if remember our a can't be 0, so a can't be 0. Yes. So if A cannot be 0, then you'll find that maybe this, actually, if this can't be 0, let's, for simplicity, let us say that this cannot be 0. Remember what we had up there? We said A is equal to negative B. So if A is equal to 0, this one can't be 0. Let us assume that this is not equal to 0, and this, for it to hold, also this must not equal to 0. So C1 exponential PCT plus D exponential negative PCT is also not equal to 0. Okay, so if it is not equal to 0, but A is equal to 0, that means our B is equal to 0, which leaves us with, a 0 answer. So if we are having finally that u x of t, okay, uxt is equal to 0, this is telling us at a point, this is at a point when the string is stationary. When the string is stationary. So we discard this condition since it does not give an oscillatory solution. So let's also try when nu is equal to 0, that means p squared obviously is equal to 0. So when it is equal to 0, you can obviously see that also it will give us things like this. We are going to have x double prime equivalent to 0. So if x double prime is equal to 0, if I integrate this, I will have x single prime equal to equal to a. Then I'm talking about if I do the integration. Okay, so if I do the integration, x single prime is equal to a, and therefore x is equal to ax maybe plus b. So I will have such a solution, and then t. Okay, if I have t also the same is equal to 0, then I'll have t maybe is equal to let me say cx plus d. So if I multiply these two, I'll find that generally I will not get a solution that is desired. You can look at it. So uxt equal to ax plus b into cx. This is ct plus d. So if I put in boundary conditions at x is equal to 0, then I'll have b, okay, and this is equal to 0. So I'll have b into ct plus d equivalent to 0. So now that means b can equal to 0. So if b becomes 0, and also I put in, I will have, so okay, I will have uxt equivalent to what? To ax then times ct plus d. So let's apply now the another boundary condition, ult. This becomes this is going to be al ct plus d and is equal to 0. So we know that for it to hold, this can't be 0. So I'll have a is equal to 0, and then therefore this will again give us a non-oscillatory because a is equal to 0, b is equal to 0, and so you'll find that uxt, okay, will also equal to 0. That is when nu is equal to 0. So this does not give the desired solution. So this leaves us with the only option, case 3, where nu nu is less than 0, that means this nu will equal to negative p squared. So what does that give us? Now it is going to give us t double prime. Remember, t double prime out of t was equal to what? Was equal to c squared, and now p squared. So this is going to give us what? This is t double prime plus c squared p squared t, and this is equal to 0. So if I talk about the auxiliary equation, m squared plus c squared p squared is equal to 0, then I will have m equivalent plus o minus j pc. So if we do that, then that would leave us with a solution that t is equal to a cos pt plus b sine pct. Okay, so that is one solution, and this is actually very nice because it is showing us some oscillatory components. Then x double prime will also equal to p squared negative times x. So x double prime plus p squared x is equal to 0. And what would be the auxiliary equation? The auxiliary equation would be m squared plus p squared. So if it is equal to 0, then m will be plus o minus j p. So meaning that the solution x will be also, let me consider c, maybe c cos px plus d sine px. So generally the solution is going to be u is going to be, I will have a cos pct plus b sine pct. Then I multiply it by c cos px plus d sine px. Now I start applying the boundary conditions. So apply the boundary conditions. So the boundary conditions that I have is that at x is equal to 0, okay, at x is equal to 0, the motion is also 0 because the string is stationary. So what is that going to give us? So if I put in 0 here, and I will have a cos 0 plus b. This is going to be c, c, then plus 0. So I will have 0 is equal to c plus 0 because the sign of 0 is 0. So times a cos pct plus b sine pct. Yes, so what does that mean? C can equal to 0. This cannot be equal to 0 if we are talking about this solution to hold for all values of t. So we are saying a cos pct plus b sine pct cannot equal to 0. So if it cannot be equal to 0, then c is equal to 0. So what does that leave us with? The solution will be ux is equal to, if c is equal to 0, I will have d sine px, okay? I multiply it by a cos pct plus b sine pct. Okay, so I also need to apply another boundary condition. Another boundary condition is going to be what? So I have x is equal to l at t, okay? This is equal to 0. The motion is also equal to 0 at the end of the string, and therefore there is no motion of any wave or no wave propagation. So if we put in our 0 here, we would have u ul p is going to be d sine pl, then a cos pct plus B sine PCT, okay? And this is equal to 0. So if this is to hold, D cannot be 0, and this can't be 0. So meaning it leaves us with the only option of sine PL equal to 0. And this can only be possible if PL is equal to n pi for n is equal to 1, 2, 3, and any other integers. So that means P is n pi out of L. So we go back to our general equation, or solution. Then U x of t will equal to we have d sine p. Okay, let's say sine n pi x out of L, and we'll have what? We'll have a cos PCT plus B sin PCT. Okay? Now, let's consider initial condition. So, initial conditions, we have the fact that maybe before that we can do this. Let's first distribute that D inside so that we have generalized constants. So I'll have U xt equivalent. So if I get D times A, I'll have AN cos PCT plus BN sin PCT, okay? And then sin n pi x out of L. Yes. So once we are there, we can now apply initial condition. So when we apply initial conditions, we have the fact that at t is equal to 0, u x of 0 is equal to f of x. Yes. So I'm going to put in a 0 here. I'll have a n, okay, plus 0, and I'll have that function. So I'll have f of x, therefore, is going to be, if I substitute it in here, this is going to be an, okay, times 1, then plus 0. Okay, then times sine n pi x out of n. So if we say these are many values, then f of x will therefore equal to sum from n is equal to 1 up to infinity of an sine n pi x out of L. Yes. So let's look at del u del t when it is equal to 0. This is equal to g of x. So let's now do the differentiation of this component with respect to, we are going to differentiate with respect to t. So when we differentiate with respect to t, I'm going to have a negative an sine PCT, obviously with the PC at the end. Then I'll have PCBN. So let me do the differentiation. So del u del t, okay, is going to equal to n is equal to 1 up to infinity of what? Remember, this sine n pi x out of L is a constant now if we are differentiating with respect to t for partial derivatives. So this is going to be multiplying into, we have a negative an, okay, PCT, okay, yes. Then this is sine PCT, then plus, now BN PCT cos PCT. Okay, so when we put in This can't be PCT because we have differentiated with respect to T. So the T will disappear. So let's move. So let's put in now at T is equal to 0 for this. So del U, del T is going to be what? So I will have summation n is equal to 1 up to infinity of sine n pi x out of r. So this is not there. So this is there. So let's write. So this becomes 0. Then we will remain with this. So times bn pc, and this is 1. Okay. So we are told that this is equal to gx. So, but remember we had said that P is equal to n pi out of L. So I can substitute this in so that we see ourselves, okay, with P going away. So G of X will equal to the sum from n is equal to 1 up to infinity of sine n pi x out of L times what? Times Bn, okay, times we said this is Cn pi out of L. So we can put this outside and we shall have G of X, which is going to be what? I will have C n pi, I will have C pi because n will remain inside. But if we are talking about a variable being x, so we can still put it outside so that it becomes Cn pi out of L. Then we take our sum of these components from n is equal to 1 up to infinity of Bn sine n pi x out of L. Okay, so how do we determine An and how do we determine Ax? So An, as we have seen, for An, we have sine n pi x out of L. So this is going to be equal to 2 times the mean value. So we are talking about now the Fourier coefficient. So mean value of f of x and what? And sine n pi x out of L. So meaning the An is going to be 2 divided by L, and this is for 0 to L. So from 0 to L of f of x, then sine n pi x out of L dx. Then Bn is also going to be twice, okay, the mean value of gx and gx and what? Gx yes, this is going to be gx sine n pi x out of L, but obviously when we are talking about L divided by C n pi. So what we are saying, we are just going to make Bn the subject. So this is going to go the other side. We multiply by gx, and this this L will multiply here and C n pi go down. So meaning this Bn is going to be 2 out of L, okay, times L out of C n pi, then from 0 at L of gx sine n pi x out of L dx. So once we obtain those coefficients, so once these coefficients are obtained, we substitute back to the general solution. So the general solution, therefore, is going to be, we are going to have it as u, okay, of t. So you'll have u xt will equal to summation. The summation, we are going to have an from n is equal to 1 up to infinity of an cos n pi out of r, ct, then plus bn sine n pi ct out of r, okay, then times sine n pi x out of r. So that will be the general solution for the 1D, for the 1D or one-dimensional wave equation that we said that this is their 2 del x squared is equal to 1 out of c squared del 2u del t squared. So this has been a very lengthy problem, but is worth it. So once you go through it and understand every bit, please you'll be able to find that this is very easy. So in summary, what we can say is that to solve this problem, especially the one-dimensional problem for wave equation, you have to identify clearly the initial and boundary conditions. Yes. Then assume a solution of the form u is equal to xt and express the equations in terms of x and t and their derivatives. Then what you do next is you separate the variables by transposing the equation and equate each side to a constant, like we did say the constant that we made to be nu. Then you get two separate equations that are ordinary differential equations. You have one in x and another one in t. Then you let that nu to be negative t squared to give oscillatory solutions. Leave alone the other two conditions or cases where we had nu is equal to 0 and nu greater than 0. So it is only nu less than 0 that is always going to give you a desired solution. Then another point is that the two solutions are of the form a cos px b sine px and t will equal to cos cpt plus d sine pct. So you'll find that you have the general solution that we earlier on put down here, okay, is up here. So then you apply the boundary conditions to determine the constants a and b, and then from there you apply the remaining initial conditions and boundary conditions to determine the coefficients an and bn from these equations that we later on listed down. An equal to 2 out of r, integrating from 0 to r of f of x sine pi sine n pi x out of r with respect to x, and then bn equivalent to 2 out of cn pi, integrating from 0 to r g of x sine n pi x divided by r. And then from there you can substitute your coefficients in the final equation, and then you'll have the general analytical solution to the 1D wave equation as earlier on